Good evening. Today, I'm going to be talking to you about my Woodrow Wilson research, which centered around the construction of an electrospray ionization source for magnetic bottle photoelectron spectroscopy of cluster anions. And if you're like 99% of people in this room, you have no idea what any of those words mean. So, what is photoelectron spectroscopy? With anion photoelectron spectroscopy, we're going to be looking at anions, and we're going to look at them by using this, a laser, to shoot a photon of light at them. This is going to cause the anion to release an electron, which we'll then analyze with this magnetic bottle energy analyzer. This will produce this, a photoelectron spectrum. While on the surface this may look like just a bunch of blobs, squiggles, and lines, in reality, this spectrum contains a lot of valuable information about the electronic structure of the corresponding neutral to this anion. The electronic structure governs everything we do. Fundamentally, the way two substances will interact with each other is governed by the electronic structure. The electronic structure will tell us about solvation rules, or whether a substance will make a good battery electrolyte, a good alternative fuel, a good catalyst. And photoelectron spectroscopy provides us with a way to learn about the electronic structure, making it very powerful. So, what is electrospray ionization? Electrospray ionization is a technique that lets us take macroscopic quantities of things present in the solution phase and transport them to the gas phase at high vacuum, where we then can conduct photoelectron spectroscopy. So electrospray ionization works by taking our analyte solution, shown here as a bunch of yellow dots, the analyte, what we want to look at, and blue blobs, the solvent. We then take the solution and run it through this, a charged stainless steel capillary at about 5 kilovolts. There's a small hole at the end of the capillary, and that produces what's called a Taylor cone, the electrospray, right here. So as you can see at the beginning of the spray, the droplets are rather large. They consist of many analyte molecules and a whole bunch of solvent. But as we move further down the cone, eventually all the solvent is gone, and we only have the analyte left. That's exactly what we're looking for. By coupling electrospray ionization and photoelectron spectroscopy, we can take systems that we have in solution and transport them to high vacuum, where we can do energy analysis to find their electronic structure. So this is a schematic of the electrospray source. Here's the electrospray needle we were talking about earlier, the desolvation stage, where most of the solvent is removed, and these, the ion guides. The ion guides work by using an electric field that oscillates to confine the analyte as we slowly move it down the beamline. Electrospray ionization happens at room pressure, so at the same pressure that we're currently standing in. However, in order for photoelectron spectroscopy to work, we need to be at ultra-high vacuum. So 1/millionth of 1/billionth of 1 atmosphere. So 10 to the minus 8 torr, or about 11 orders of magnitude different than the room we're standing in now. So these ion guides help us move slowly from room pressure down to high vacuum. Then we come upon this, the quadrupole deflector. The quadrupole deflector bends the anions that we want this way. Anything with neutral or no charge moves straight on through, and anything with a positive charge will be bent the wrong way. Neutrals and cations are thrown away, whereas the anions that we want proceed here to the ion trap. The ion trap is really the heart of the entire apparatus. Electrospray is a source that's continuous. It produces ions all the time, but at a weak rate. The ion trap allows us to accumulate all those anions and then release them all at once. We need this because our magnetic bottle spectrometer is intrinsically pulsed. It requires that it receive a bunch of ions all at once instead of a steady stream over time. So, how does an ion trap work? An ion trap is like one of these, a bucket at your local water park. The electrospray slowly fills the bucket, and then when the bucket's full, boom, it dumps all the water at once. The ion trap is much the same way. The electrospray fills the trap, and then 10 times a second, we dump all the ions out at once. So here's the real problem. If you want your very own magnetic bottle photoelectron spectrometer with electrospray ionization, you can't just go out and buy it at Walmart or order it on Amazon Prime. You have to build it. So here I am, hard at work, constructing a focusing lens on our chemistry department lathe. Here I am grinding a tool to cut the O-ring groove that we're going to use later. And here's a before picture. So as you can see here, the photoelectron spectrometer, at least the front half of it, is already existing. We can see it right here in this picture with these stainless steel chambers. However, what's eventually going to become the electrospray is currently taken up by this set of scaffolds, ladders, and caution tape. Here's what the source looks like now, a little bit different. So as you can see here, right here is the needle that we were talking about earlier, where the spray actually happens. Inside this chamber here is the quadrupole deflector. These are 3 home-built power supplies that run the ion guides. And here is the controller that tells the ion trap when to release the ions. Here's a picture of our first ion guide. Here's one of that focusing lens I was making earlier, along with its holder and electrical connection. And this here is the aperture plate. Remember earlier, I discussed we had to move the ions from atmospheric pressure to high vacuum. This is really the trick to making that happen. All the ions must pass through this small hole in the middle. They're focused by the ion guide to permit almost all of them to pass. However, the hole will only permit a small amount of ambient gas to pass as well. Once we pass through about 4 of these, we'll go all the way from room pressure to our 1/millionth of 1/billionth of 1 atmosphere. So here's a picture of the ion trap installed and ready to run. And this is where the magic happens. This is the photoelectron spectrometer. This here is the magnetic bottle. It's about 6 feet tall, so as tall as I am, sticks about 10 or so feet up into the air. And this is where we do the energy analysis and make the photoelectron spectrum. And here I am, hard at work, tuning up the beam power on our new source. So, what systems are we going to look at with this new technique? Ionic liquids are, you guessed it, liquid at room temperature, unlike most ionic compounds, which are like table salt, solid at room temperature, and you have to heat them to around 1300 degrees Celsius to be able to liquefy them. Ionic liquids have many interesting properties in the areas of solvation and catalysis, but not much is known about their electronic structure. We want to use electrospray ionization to transport them to the gas phase, where we can then do photoelectron spectroscopy and learn more about them. Similarly, lithium batteries are all around us. From your iPhones to your electric cars to cordless drills, lithium-ion batteries really make the world go. However, not much is known about the electrolytes, what helps carry the charge throughout the battery. By using electrospray ionization, we can transport these electrolytes to the gas phase, where we can then do photoelectron spectroscopy. This information could potentially aid collaborators or other scientists in developing new, better battery electrolytes. These here are ligated aluminum clusters synthesized by a collaborator down at the University of Maryland. They are extremely high in energy and show great promise in the area of alternative fuels. However, not much is known about their electronic structure. Photoelectron spectroscopy can get us there. Interestingly, these ligated aluminum clusters are actually exceptionally difficult to analyze due to their air sensitivity. We had to custom build our source with this in mind, and to my knowledge, it is the only source in the world that has this ability to do air-free compounds at this level. And of course, we can analyze everyone at Hopkins' most favorite thing, biological molecules. So, thank you very much to the Woodrow Wilson program. As I'm sure my mentor will tell you, the most expensive part of building any source like this is not the parts, it's the people. Somebody has to design it, they have to build all the parts, they have to put it all together, they have to test it, they have to run experiments. People cost real money. Wilson was able to help me pay for a lot of my living expenses while I was constructing this source. They also paid for several parts that are now on the beamline, and no, you can't have them back. I'd also like to thank my mentor, Kit Bowen. This project certainly would have not happened without his help and guidance. These projects certainly do have their stumbling blocks from time to time, and my mentor was a very valuable source of advice. I'd also like to thank my coworkers. You aren't born knowing how to build one of these things. I certainly didn't come to college knowing how to build one of these things, My coworkers were a great resource in terms of helping me learn what I needed to learn in order to make this project a reality, particularly Evan Collins, who we worked together every step of the way from designing, building, constructing. Thank you very much.